Why does the universe seem to be missing 2/3 of the lithium it was supposed to make at the beginning? In the energy filament theory, lithium is not a simple leftover ingredient from the Big Bang but the most temperamental lock pattern among the light elements. So a small change in the early universe's tension could slash its success rate by about a factor of 3. Textbooks say the first minutes after the Big Bang cooked up 3 main light elements: hydrogen, helium, and lithium. And that hydrogen and helium match theory pretty well, while lithium stubbornly shows up at only about 1/3 of the predicted abundance. So for decades people have tried tweaking parameters and code to push the numbers together, and the lithium line still refuses to move. In this picture, that mismatch is not a bug. It is a clue about how hard it is to lock a lithium atom into place compared with hydrogen and helium. Think of every stable atom as a rhythm lock. The spins, magnetic moments, and phases of protons, neutrons, and electrons have to land in the right timing window so that all the internal beats line up and the whole structure can hold together. Hydrogen is the easiest lock in the set, like a 1-digit passcode. Helium is like a double door with 2 very forgiving latches that will close as long as things are roughly symmetric. But lithium, even though it is still light, it is the pickiest of the 3 and needs several separate checks to pass at once. For lithium to survive, the 3-loop filament knots inside its protons must sit in the right orientation. The reversed bridge inside each neutron must be stable enough. The overall nuclear tension must sit inside a narrow, not too tight, not too loose windows, and the phases of the electrons near the nucleus must fall inside a matching zone as well. So the atom is more like a security gate that wants the right password, the right face, and the right access card at the same time. Now rewind to the early universe in this language. The energy sea was tighter, the tension was higher everywhere. Proton knots were pulled harder, neutrons were more easily shaken. The nuclear environment was stiffer, and electrons were still running on an older, slower rhythm. In that high tension setting, the timing windows for these locks narrow. What used to be a broad doorway becomes a thin slit. For helium, which has a roomy, symmetric lock, that does not matter much. Its broad double door stays open through most of the Big Bang fusion rush, and the universe makes plenty of it. For lithium, the situation changes drastically. Its proton-neutron structure is under extra strain. Its sensitive latches are operating with narrower timing windows, and the electrons that would later help stabilize it are not yet in their modern rhythm. So only in rare, just right moments do all the internal checks line up and let a lithium nucleus pass. Almost lithium attempts fall apart or never quite fully lock before the hot early plasma moves on. When we sit here today with our present-day particles and run the clock backward with their current properties, we computed an ideal lithium abundance. But the real early universe was using a slightly different version of those particles and a higher tension energy sea, which effectively closed the lithium gate for about 2/3 of the time. From this view, the lithium problem is not a random failure of the Big Bang recipe. It is the nuclear physics layer in a bigger stack of evidence that particles and their locking rules have been slowly evolving with the universe's tension. Alongside redshifts in light, subtle spectral drifts, and weird rulers in distant molecules. Tap follow, share it on New Physics, Clear Universe.